but it does not matter because if you work on C, you can easily do the one on R. Then we now define L infinity of S of V to be equals to the set F from S to V such that here exists M positive such that for all f in S, norm of f of x with respect to V, norm V is less than or equal to M. Then he just gave a side comment. You can actually check that this guy here is this guy with the norm is a vector, is a norm space where for all f in L infinity of SV, norm infinity of f is equal to sup S in S of norm of f of in V. This is definition. So the first question goes thus: prove that the uniform limit of a bounded function bounded functions is bounded. Question number 1. Prove that uniform limit of bounded functions is bounded. That is more precisely Fn be a sequence in L infinity of SV. Suppose f is a function from S to V. And
well, it seems the question is very long too.
yeah, it's just a setting. Normally, like he said, whenever he's giving, you don't need to cram out this definition. Okay. So these are like definitions you used to put. This is just where the question started now. These are definitions you use when proving the question. You just define what this guy is, which is what we are using here. Right? He defined what, he gave what V is, gave what S is. And that's all. Suppose like this, and that Fn goes to F uniformly on S. That is Fn going to F uniformly on F means for all epsilon positive there exists n bigger than 1 such that for all S in S, for all n uniformly bigger than n, norm of fn of s minus f of s then prove that f is in L infinity of SV. That is, f is bounded. You want to prove that f is bounded. This same thing that we are going to use, we have used it countless number of times. It's just easy for you to know. You want to prove that f is bounded, right? Mm-hmm. More like you want to bound f above.
Mm-hmm.
More like you want to bound f above.
Mm-hmm.
Now, remember what we did before. You know that the same f, I can add 0 to f by subtracting some g and adding the same g, right? And then I apply triangle inequality here plus g. So if I have a bounded function and I have that this is bounded, the whole of this can be bounded. So it's this same technique that we are going to use here. I'm going to show that f is bounded.
Okay.
So yeah, that's what I'm about to apply. But the direction of this proof, you won't just let epsilon be given. This time around, you fix it because you need it to bound. Suppose this is, now look at the idea. Suppose this is Fn and this is still Fn. I know that this guy is Fn here, and I know that here is what? Fn. We already have that Fn's are bounded. That means I can bound this guy. And we have that Fn goes to what? F. That means I can use a particular epsilon. If I fix a particular epsilon, I can bound this guy too. So that is the idea. If I now come and say because Fn goes towards F for
all epsilon.
M naught positive fixed. Since I know that for all positive number there exists an n, so for this m naught positive, choose a natural number greater than what? 1, such that this is uniformly. We have uniform limit here. So by uniform definition, we have such that for all s in S, for all n bigger than or equal to what? This norm of Fn of S minus f of S in V is strictly less than what? M naught. This is true, right? So, in particular,
Does that show the boundedness? What you just showed now?
no, this is just, I just use property of uniform convergence.
He just replaced the M with epsilon.
Yeah, I just replace epsilon with,
Okay.
of course, you can use epsilon naught here. But the idea is that I want this guy to be fixed. I want you to see it like a fixed number because I need a fixed number to bound whatever I want to bound. So this happens for all. You see that this does not depend on x, and it does not, of course, it doesn't, this n here does not depend on x. So it means in particular for this capital N, right? I have that for all S in S, norm of Fn of S minus f of S is less than what? Epsilon naught. So this is no longer, this is now a particular Fn, but Fn is in where? L infinity of what? SB. So choose again. M, yeah, I can now call this one M1. Such that for all S in S, norm of Fn of S with respect to what? V is less or equal to M1. I call this 2. I call this 1. This is for a particular number. This is for what particular number. Now, let x be in what? X. Let x be arbitrary. Have x arbitrary, right? Norm of f of x with respect to v is exactly equal to norm of f of s minus norm of f, this n that I fixed, plus fn, this fn that I fixed with v. Applying triangle inequality. This is exactly f of s minus fn of s plus norm of fn of s in v. I apply 1 and 2. Here it's triangle inequality.
Sorry, please. From the f of x to be equals to f of x minus fn, do you just introduce the yes?
Yeah, you just introduce it.
Okay.
This and this gives you 0.
Okay.
This minus this is 0. So
Okay.
you just introduce it. You need to get
Okay.
it
So
down
using
here.
the triangular inequality
Yeah.
stuff. Okay.
So by 1 and 2, we have that norm of f of x is strictly less, because this one is strict inequality, like this one, so it's strictly less than epsilon naught plus what? M1, which I can define this guy to be n. That n that we are looking for, of course, this is positive. So what have I done? Since x in S is arbitrary, we have that for all s in S, none of f of s is, of course, even if I slap this inequality, it does not change anything. If I say something is strictly less and I say it's less or equal to, nothing has changed. i.e. f is bounded, i.e. I'm not doing like Dr. Bing, I'm writing everything. But that's what he wants.
Makes sense.
Yeah,
So it shows it is bounded.
yeah, we are done.
Not bad, Professor.
Oh, good.
The proof is short.
Yeah, that's not bad.